This is structure of discrete analysis. Structure of discrete analysis. Structure of discrete analysis. That is how you can implement a server. Because you have now the knowledge of state transform. How you can express your system, input, output, how you can express. That only you have covered. So now we will discuss how to implement discrete analysis. So, structure for the structure for discrete analysis. So, if you see here, what I'm input, this is system transfer function. This is our EECE system transfer function. What is exit? Overall system transfer function. Z transfer of the output, Z transfer of the input. Y by X. That we know. So if I give you one example, let's see HZ equal to 1 minus 2 Z inverse divided by 1 minus 3 Z inverse plus 5 Z to the power minus 2. Let's see, this is a transfer function, overall transfer function. Transfer function is Z transfer of the output, Z transfer of the input, like this. If I just cross multiply, so this will give me YZ minus 3 Z inverse YZ plus 5 Z inverse YZ equal to XZ, I'm just cross multiplying XZ minus 2 Z inverse XZ. It's okay? Let's write, please write. So this is an overall transfer function, y by x. So let's cross multiply y z minus 3 z inverse y plus 5 z to the power minus 2 y plus 5 z to the power minus 2 y equal to xz minus 2 z inverse. Let's see. Yes, xz minus 2 z inverse. Okay. Now you should answer, if I do the inverse Z transfer, you should answer inverse Z transfer of this line. What will happen? YZ, Y1. Next, Z3, Z inverse, YZ. What will be the inverse Z transform? Z to the power minus 1. It's a very long. Don't we say this Z inverse? I told you earlier, D upward. So this is the D operator. Draw this separately. X and Z inverse will produce X n minus. Don't mistake. Z inverse delay will produce x n minus 1. Basically, xn is xz. And this is Z domain. This is also Z domain. These two time convolution Z domain multiplication. So the output is Z inverse xz multiplication, which is x n minus 1. Okay? Which is x n minus 1. So if you have two delay operations, Z inverse, then again another Z inverse. So xn, then what will happen here? Xn, Z inverse, again another Z inverse. So here, x n minus 2, exactly, because here is xn minus 1. Then x minus. So this is the operations. So now we can write, okay, fine. Ym minus 3 yn minus 1 plus 5 y n minus 2 equal to xn minus 2 xn minus 1. So this is input-output relationship. Linear, constant coefficient, difference equation, not differential. You have a lot of differences. First difference, second difference. This is first difference. One sample linear, second difference, two sample linear. So linear, constant coefficient, difference equations. It's right here. Yn equal to what? Almost zero. So Yn equal to 3yn minus 1. 3 yn minus 1 minus 5 yn minus 2 plus xn minus 2xn minus 2 xn minus 1. This up to this we know this. This is input-output relationship of the system, input-output relationship. Now, I want to implement it. Let's see in a breadboard. You need wires, headers, enablers. Let's see. I want to implement it. Okay? How do you do it? Carefully check. You have to make Yn from Excel. Input output. From Excel, you want to produce Yn. You want to produce Yn from this Excel. The question is, how can you produce it from Excel to Yn? Let's see. Yn is equal to 3 yn minus 1 and 5 1 minus. So you need this term to produce Yn. If you want to get Yn, you need this one, Yn minus 1. Okay? Don't draw it now. You need Xn. Okay, fine. I here Xn is here, so I can get Xn from here. But I need Yn minus 1. How to get Yn minus 1? How to obtain Yn minus 1 here? How? You see, we have got set inverse. Means you need a delay element. So, if somebody gives you a delay element, you'll be happy to find I can insert Yn here, immediately it will give me Yn minus 1. Fine. You also need Yn minus 2. You see, you need Yn minus 2. Okay. You need Yn minus 2, another example. You need another Z inverse. You need another Z inverse. That will give you Yn minus 2. It's up to you. You can draw here and then plan drawing this. So your output is equal to your Yn is equal to. So here you see, I just touch it and collect it. This is not an adder. It's not an adder. It's a collector. He's just collecting the data. It's not an adder. It's just a collection. So what is adder? You must have read by this time. Adder means, let's see, you have an input here, another input here. This is V. This is V1, this is V2. So your output have to be V1 plus V2. This is collaborative. This is an adder. 2 input, 1 output adder. 2 input, 1 output adder. Generally the adder is like that. 2 input, 1 output. So V1 plus V2, you can get W. And notation wise in signal flow graph, some people they will use this type of dot to show you what is happening. Some people they show, okay, this is V1, this is V2, this is W. V1 plus V2, this is W. some people they show, okay, this is a adder. First, just one line here, one line here. So this is an adder. Your output will be V1, V2, W. W equal to V1 plus V2. But if I write it like this, even I give the circle or dot here, I write here by V1, V2, W. What is W? Suppression. What is the difference between two pictures shown there in signal flow graph? You see, in signal flow graph, if you draw like this, V1, V2, this is adding like this. This is added. Here, no, it is just a collection of data. V2 means from here you are collecting. In fact, this is one line, one bar, one line. You are collecting the data. V1, W, all are same. This is same line. Is it clear? In fact, it is not same. All they are same lines. It's not an error. Not an error. Please don't mistake. It is not an error. It is not an error. They all are same. Same point. WWW. You just collect. All these 3 points are same. Is this okay? There is no separate. Some books they use circle or they made it like plan, but it's not mandatory. People will understand. This is input, and this is scanner. This is just a collector fish. Now you should answer like here. This is a collector. Whatever is coming, you just collect it. This is okay. This is not an error. Okay? This is not an error. This is an error. What you have to add? You have to add X7. You have to add X. Okay. X will come here. You have to get 3yn minus 1. So this is yn minus 1. Exactly. You have to bring it from here and bring it there. And multiply by 2. Then yn minus 2 is ready. You have to bring it exactly minus 5 multiplied and then bring it here. Yeah, you can directly bring it here and add. But in that case, already somebody is coming here, like X7. Somebody is coming here. If you also bring it here, so there will be 3 input 1. Rather than doing that, you can leave it as it is. You can add it here. Here. So you bring it here. One input, another input, they will add and go here. All the same. So that you don't have to use 3 input 1. All we have used here 2 input 1. So you are now close to your output, yn. At this moment, yn is equal to x7 plus 3yn minus 1 minus 5yn minus 2. Yn equal to 3yn minus 1 minus 5y minus 2 and x7. I just need one more term. X minus 2, x minus 2. So find exactly z inverse. So bring it here and it is 100%. So in a similar manner, you can use a z inverse and that will give you xn minus 1 multiplied by minus 2. You multiply by minus 2 and bring it here. So this is xn coming here. Is this an adder?
No.
Adder? No. This is just a collection point. So this is xn. This is also x coming here is x. And here minus 2 xn minus 1. this one. So now is an add. So this one x and this one minus x over this one will add. Now it is complete. Why? I mean, if there is another term, yeah. So in my case, I left it. I don't have an answer here. There will be another term that will be here. Minus 2. I can see plus b z inverse. So here there will be plus 3 x minus 2. One more term will be here plus 3 x minus 2. So if you want, you can add one more term, z inverse x minus 2. So that is plan 3. Okay, plan 3. You go here and this. Finish. That means you see, whatever so far we discussed, it is very apparent. But we need z to the power minus 2 to produce x minus 2. You see, if you need x minus 2, you need 2. Is it clear? This is called implementation of your transfer function. You need a breadboard. What else you need? You need delay. Okay? So you need delay. You need what else? Delay. What are the other things? Delay and then adder. Simple. Adder. And what is this? Gain. Gain. Exactly. Gain or multiply. Multiply. For gain. Obviously, this is for gain. These are the things I'm somewhere finish. If you ask me, how this delay looks like, this is delays are ice. Like adder is an IC. IC. So it has some pins, 2 input, 1 output. IC. So adder, multipliers again, and delay is memory. You see, if you are here, you need some delay. I told you why. Because if you want an output y10, you need y9, 1, y8. These are previous instances, y9, y8. So who will hold these values? It's already y8, y9 got delay element, so that they will hold those values. So when you are here y10, you need y9, 10 minus 1 9. Y9, so you need delay. So for causal system, we are dealing causal system depends on percent and force. So if your system is causal and if your system depends, it's quite natural your system will depend on past values. In that case, you cannot avoid delay. Is it clear? Delay is mandatory. If there is no delay, that means input out. So whatever you are getting, output is just multiplication. If it doesn't mean simple. Another important thing here, if there is just don't draw it, I'm just telling. If there is no delay, you draw like this here. You draw like this. You draw straight like this. So what does it mean? X minus x. What is this value? X. Forget about this. X is going here again X. X is already here. Why you have to draw another? So this type of group without a limit, you see this. Whenever there is a loop, there should be a delay. A loop without a delay is totally meaningless. I have one picture, I guess, a loop without delay. If I want to go like this, you see, this is very confusing. We'll do it later. Here is a loop. You see, where is the delay? There is a problem. There is a loop. There is no delay. No delay. No delay. No delay. Spring color. There is a problem. So that will solve later. So what is our up to this? What we have learned? Okay, fine. That if you are given input of relationship, if you are given SCTU, so now I hope you understand how to implement this. Now look at this particular circuit. So closely look at this. So we'll do one thing. Here's the jet inverse, the price. So now, this one, let's say, this the whole thing. I am going to match with my transformer. What are the values here? This minus 2, minus 3 came from x. You see, minus 2 plus 3, they came from coefficient of s. So if I look at here, original explanation, system function. I was given hz, output jet transform, input jet transform. Basically, jet transform is a polynomial of z. So this is output, this is input. If you look at this output, this is more like this. V0, V1 z to the power minus 1. So if you break it, it will be like 1 minus A1 z to the power minus like this. So instead of that, I have chosen this example. This is easier to understand. Basically, 2, 3, these are coefficients. In terms of formula, they are B. So you should give me answer. What is the value of B0 here? B0, if you compare this, B0 here, 1. E1 minus B plus. So B0, B1, now, carefully answer me. What is the value of A1? 3, not minus. Because in formula, there is a minus. So minus A1 minus 3, A1 equal to 3. So you can tell me why they intentionally put minus. The reason was when I went from here to the next line. So you have seen this cross multiplication will give me y minus something. Ultimately, I will keep y in one side and all of them in other side so that they become plus. That was the obvious. Why I am again telling this? Because in some books they write plus. It's not a big deal. In that case, your A will be minus 3. Now, with the minus sign, this A is plus 3 millimeters inside that. So, I hope you understand this one also. So, your A coefficients are 3 minus 5. Let me check. Yes. 3 minus 5, all these are coming from these are coming from A polynomial, and this minus 2, 3 coming from B polynomial. We may consider this as a block and consider this another block. So input is coming, then a big block, then another big block, output is produced. This one is B, this one is A. If somebody tells me, hey, if you just interchange here and here, what will be for? You see, this is A, this is B. Your Y, Z is equal to X into BZ is it. X into BZ into S. Here, your Y is equal to X into A into B. Is there any difference? No difference. So you can do that. If you are doing an linear system, that is linear system, there is no linear. It's hard to do that. So people they're thinking to do that with a purpose. You see, it's like just like magic. If you do that, you bring this in this side and bring that in the other side. So what we have? Due to time, I just use this here. Then you'll understand. Let's think. That block is now bring here. And this block is brought to test. So this one is coming here. So the whole chunk is coming here. So this node will be now positioned just beside Y. This one will be positioned Y. And this node will be now positioned beside X. Let's see. Yes, this node is going upward 3. So this node will be positioned beside X. X was previously connected with the J inverse, but now once I took it that side, it will be just a line, then J inverse. You see, it's a line, then J inverse. A parameters, yes, they are A parameters. A1 and 2, A parameters. And this one, I told you, that block is less now here. Is this okay? We can show these are exactly equivalent. It is shown here. I'm just ignoring them now. So these two are equivalent. Don't worry. But the operations you have performed just figure that. So this is something this. Now you close to this side. You should answer. Last class, I got the answer. What is happening with your input here? Carefully check. This is your X coming here, X. And something is coming here. They are denoting this as W. So if this is W, so is this an adder or connector? Connector. Because something is coming this direction, this is leaving, this is also leaving. So this is a just connecting this point. If this is WL, what is the value here? WL. WL. This one is WL. WL. All W. Okay? So in this circuit, can you see any redundant operation? Unnecessary operations? Closely watch. So you have WN all here, all you are connecting, then you are doing something, bringing it here, going. So is there any unnecessary operations? Exactly. Very good. Exactly. You are performing the inverse. So W and here it is W minus 1. So why you have to again just select it from there? Don't use this. You understand? Same thing. Once it is Wn minus 1, your desire is to produce Wn minus 2, it is no more needed. You can just collect it from there. And what happened? You are removing 50% delay. Can you imagine? So you are actually, if a circuit needs 10 hours operation, you are using half, 5 hours. Huge reduction by simple just changing here and there. That's why this chapter it teaches you implementation as well as efficient implementation or different types of implementation. There are different types of implementation. Okay, the objective. So what we take now, so on this line, target versus going. This line, target versus going. You know, in the box here, it is a signal flow graph. Second blocks. Currently it is block diagram, but in signal flow graph, you don't need those blocks. It's a simple block. Now, please draw this picture. From here to that picture. From this picture to that. That means this x to y, one line. X to here, y. Previously there was 4 lines. Now let's read this line, and this line. The middle line will produce delay, get inverse. This one. Another get inverse. Another get inverse. So if this is Wn, this one will be Wn minus 1. And that have to connect and give it here, give it there. So you can give it here and give it there. With coefficient A1, A1, B1 like this. And this one is outside. So something input, this one is, you see, input. That is good. One input here, one input here. This is good. I hope now you understand what is going on. So this one is going here, this one is going here. Here, one is coming, one is going here, one is going here. Error? Is this an error? No. 2 input, 1. It's not 2 input, 1. 1, 4. It's not an error. It's not an error. This one error. 2 input, 1. Okay? This one. Input. No, 1 input, 2 error. This one error. Why? This is coming. This is coming. 2 input, 1 output. Error. This one is an adder. 1 input, 1 input. 2 input, 1 output. Here they have written very nice. But when you draw signal flow graph, you don't have to explicitly write. People will understand. When 2 input, 1 output. Adder. 1 input, 2 output, not an adder. If you have to change A minus B or something, you'll be here. Like plus minus B. Don't put there. That is an add. If you want to do subtraction, it's there. Just make the coefficient negative. That's it. Still, you are absolutely correct. You are going to ask, X was delayed. Y was also delayed. You see now again, X is delayed. And the Y, here, this Y, this is same as here. This one, same. So, two input, one output. So, what is happening? W is going. This W is going here. So this is W. Your Y is W plus here. Something is there, something here. So what she's telling that still will get Y minus 1. That is average. Whether still we are getting Y minus 1 function. Let's do it. Then we numbers. So the question previous transformation HZ was PZ by AZ something like this. Now, whatever you draw here, is it the same or not? Let's see, this is W. Then your Y equal. You have to answer me. What is your Y? This is Y. So what is the expression of Y? So Y is basically W. Y is basically W. But there is an error. W plus. Now you tell me what is coming in this path? What is this? What is this? W n minus 1 into V1. And also, this one is coming. Exactly. N minus 2B. Clear? So your Y will be equal to Wn plus V1 Wn minus plus V2 Wn minus 2. Like this. Now if I do the Z transform, this will give me Wz. So Yz, Wz. What is the Z transform? V1, then Z inverse. There is a Z inverse because it is n minus 1 Wz plus V2 Z to the power minus 2 Wz. So I can write it's on the side of I'm sure. And cafe. So this one is equal to Yz by Wz. Equal to, if I just say Wz out, it will be 1 plus V1 Z to the power minus 1 plus V2 Z to the power minus 1. Now, if I ask you to write an expression for this part, this is W, this is W, this is actually 1. So this one is also W, all W, this is W. So I want to write an expression for W. equal to xn in this path. Now, plus, you have to say wn equal to xn plus a1 w this one was 2 to that important a2 w n minus 2. So now, if I want to write the expression of this h equal to hz equal to y by x. Actually, I have y by w. So I can write y by w into w by x. W cancel y by x. I can write y. That means I have the answer for y by w. Y by w. I have the answer. I have the answer for w by x. It is w by x. So we do that example for wz xn a1. What is this? Z inverse wz. If you spell out, good for you. A2 z to the power minus w. So I need w by x. I need wz by x. I can think all of w here, w. I think that in one side, that will be 1 minus a1 z inverse and then minus a2 z to the power minus 2. I bring this w on the left hand side and leave this x on the right hand side. That will give me w by z. Z by xz. So wz by xz equal to 1 by 1 minus a1 z inverse a2 z to the power minus 2. You see the same expression? If you now plug it here, and it is here, it gives exactly the same here. Okay? It's not visible by eye. You are absolutely correct. It's not visible by eye because this y is somehow getting the delay here with the help of w. Actually, is w is making this operation for y. And except one. That means what you understand, this is a unit, very easy, but this is the ideal second order block. This is the block that people they use for implementation, second order implementation. Okay? So this is a basic block. So I mean, if I now ask you if you draw an implementation for this, I'm sure you can draw this like this one. Try this with the help of this. Exactly. Draw this type of thing for this. For this. Just try to recall your BZ and S. So these are your B coefficients. And these are your A coefficients. Originally it was 1 minus A1 z inverse minus A2 z to the power minus. But this one is V naught B1 z inverse B2 z minus. Like this. So for your case, V naught equal to 1, B1 equal to 2, and this one is 1. A1 minus sign, minus sign. A, you take and then you draw. Please draw this. The second channel is you are supposed to draw. It's this part A. Without B. This is B. This is A. So A part on the bottom. You will put one meter. One meter. Why? We intentionally have used one. Okay? Note that in your exam, if this is not one, you have to make it by just taking some common factors. Let's say it is 4. So you have to just push the 4 out. Then it will be 1. And that 4 is going to multiply. That's beginners. So 1, then minus A1 minus A. See? Yes, I have one. So what is the value here? 1.5. Then this one? Minus 0. Is it clear, everyone? Just match with the ideal. Just match. Don't confuse. In our derivation, we kept line on side. That's why all 5 other they were on the other side and positive. That if this is minus, fine. I'm having minus, so this plus. If this is plus, I have to change the sign. For the denominator, for the A, I have to manage here. For the B, so B naught. Yeah, you don't have to B naught or bottom of the B naught. You don't have to bring the B naught outside. No, you don't have to. Okay? For our formula, B naught was there. If you check, B naught is there. 1 is just made here. 1 is for Y. So now there is no B naught. B naught is plus. Then our B1 is 2. Our B1 is 25. I don't have B2. So B2 is 0. B2 is 0. 0 means it's all. You don't need any where. It's just, it doesn't exist. It doesn't exist. Then just leave the 4 here. B not equal to 4. But for both of them, 4 here 5, even 4 here 5 no. Because that one will intentionally take it 1. We intentionally leave that one on that side. Already is not much the picture. It is 1. So you have to Content and gets a stuff. So it will be if it's 4 1 by 4, the outside. Another block 1 by 4. Then start like this. So this is the basic block. So it's not I'm making instead of this one, instead of power here, from power. I can be 1 minus a 1 then 3 minus 1 up to minus let's say 8 get to the minus 8. What will happen? There will be independent terms. So just for example, you can just extend. No problem, we can do that. But as I said, our another objective is to see the variations, other alternatives. We just have completed this J transform chapter, J transform, first J transform. So we can easily factor out. You can factor as far as this law is solved together, so the second order law. You should answer it. So when you are implementing your circuit, already I have given you a module, second order. You want? I just ready second order. So a lot of second order. You want 100, I can give you 100 second order blocks. So in that case, when your transfer function, the highest order is 8, how to implement it? Chapter in cascade. So just like another word. You understand? Side by side, the floor, in there, multiply this, no problem. So this is called cascade extract very easy. Yes, if it is not 8, if it is 7, no problem. You give me second order law. I have no problem give us one law. So 3 second order law. One of the clock will not have the ground wires over and 0, if it is the first order. If it is the first order, again 0, 0, finish. I just open that path. That is fine. So this is called cascade structure. So what I say, we factorize and then implement them. This is called cascade structure. Don't bother about these equations. You don't have to remember them. All coefficients. So just name it. Basically, there's together. 1 plus 1. Don't bother about this again. 1 Now you tell what the another alternatives. Because you now know the factors. You think the J transform chapter. You have these factors. This is cascade. What the no chapter really works. A factor or inverse J transform First J transform. What after doing the factor? Can you recall? So factorization. Then from first transform to the next step. First we do the factorization. Factor. So then what is the next step? For inverse J transform HF, if you want to write down the HF, what is the next? If there is one predicted arrow steps, if I give the arrow seed, then what? Yeah, so you have the arrow seed. So you have to do the partial fraction. You have to do the partial fraction. That partial fraction, is simple, but that is moving from multiplications to addition. Before partial fraction, terms are multiplied. After partial fraction, terms will be added. Then the same concept we can do it here. For example, if the order is A, if the order is A, I can do the factorization and then I can do the partial fraction. And the partial fraction result I can say how many seconds will be added if the order is 8 after partial fraction. So total the order is 8. So there will be second order factors like this. So H7, the order is 8. 8. So you do the factors. So I can pair them together like this. A1, A2, A3, like this, A4. So I can again use my similar second order block and I can use this like this. I can. Only the difference is what will be your numerator. The partial fraction. In partial fraction, remember, generally for a second order block, if you do the partial factor, let's say like this. So if you do the partial fraction, then one block here plus another block here. So each block, let's see, 1 minus half inverse. On top, this is 5 or 6 a constant. If it is z to the power minus 1, there will be z to the power 0. If your lower term is like this, upper term will be 1 minus, let's say, 6 z inverse. 1 degree will be less for the coefficient. For partial. That is all about partial fraction. It's nothing we need to describe. If I show you this is the form, your HZ would be like this. Each term will have one less. One less. If they are equal, then one constant term will be without and so now what will happen? Your this term will be parallel. Input and then like this, your output. You understand? Simple. This. So if it is 8, then 2, second order, 4, second order. 1, 2, 3, 4. So you have to add, partial fraction add. So this x will go here, output, x will go here, output, x will go here, output. All together you have to add. Then we get y. Is this clear? Parallel. Parallel means you have to do the partial fraction. Once you have the partial fraction, then all these blocks with a constant, there will be a constant term. You have to implement parallel like this. We'll do example, then we get these values. These are values, all this stuff. Different values. Practice factoring. Parallel. So this is the last one for today. The question is, you have direct. Now you understand cascade. Then parallel. Which one has what type of disadvantage and advantage? That is the question. Let's give some hints. If you are using the direct form like this, what is there? Second order. If it is 8th order in direct form, what will happen? If you continue a long. To get the output here, you have to wait. Complete this flow here, flow, all will complete it. What if any one of them, consider delay is malfunction, not proper? What will happen to your output? Output will be something different what is expected. But can you identify by what which delay was problematic? No. Impossible. You don't know which one is it. Now you come to your cascade form. Now you come to your cascade form. Any one wrong, any one delay, or is malfunction. What will happen? Your output will be different. Now, for which I am facing this problem? Very difficult. Because this one is a combined output of this plus this. If there are 100, I don't know what is happening. But you see the parallel. That's the beauty of the parallel computation. You see the parallel. Now, if one of them is problematic, all others will be acting very similarly. And you have an option to check. So this one is a very simple second order block. X second order block. You know what should it come? So in saying you can take the form. Where it is happening. You understand? Very person. But is this like this? Oh no, no. It's here. Exactly you know what it is. Each one is separate, independent. That's the beauty of parallel structuring implementation. There are other issues, implementation with issues in terms of VNSI, certainly viewers that we have covered. And another one is for parallel version. I hope you understand that the clock cycle. For each clock cycle, there will be an edge. So, one clock cycle, this will go here. Next, here. You are ready. But in case of this, right? Nothing. Whatever output is coming is useless. You don't know what they are. You understand? So that's the beauty. Like different architecture, they have different advantages. But the parallel one is very popular. They are, you know, the advantage of looking at the faults very precisely, you can identify where is the fault located. And now, one phase, one cycle, you are, not one, within few cycles, you get the very outputs. Now it's your options, how many outputs you are looking. It's not one. Then in some applications, there are some applications where they make the circuit in such a way, okay, I have 200, but even if I get 180, I am okay. Take the 180, even 280. But if it is direct or if it is less, you cannot start the job with 180. It's impossible. Oh, that's the thank you. Yeah, content views and presentations. Please,